All right, we are live, and we are going to be doing a lot of graphing today. Now, I apologize if you hear extra stuff in the background. There's just a lot of stuff going on in my house right now. So, yeah, I will do the best so that hopefully you only hear me and not the movie that's being played kind of loudly. So, all right, so we were talking about parent functions yesterday, and there we go. There's my dog starting things off bright and early. All right, so for graphing nonlinear functions, there's actually a very nice way of looking at this. But you've got to be able to look at the function, the way that it's written, and then kind of parse out what the symbols mean. Because each symbol is going to have a certain shape to it. And if we are talking about the other numbers that are there, whether it's a plus or a minus, that's going to be indicative of, typically, a movement up, down, left, or right. So if we have something that is of this form, where it's your basic function, and then you have some extra value on the outside, some constant, this is going to indicate a vertical shift. It indicates a vertical shift of k units. So whatever you see outside of the function with a plus or a minus, you're going to do exactly that in terms of movement up or down. For example, if I were to write f of x is equal to x squared minus 3. Hold on. At least once a stream I've got to sneeze. So the focus here should be on this piece, the x squared. The x squared is going to tell us our shape, and then the minus 3 that's on the outside of the square. So the square defines the shape of the function. The minus 3 is outside of the square, and so this tells me that I'm going to go down 3 units. So it's going to take the basic shape that I have for my parabola. Remember, that was the shape for the squaring function. I'm going to take this and I'm going to go down 1, 2, 3 units, and then I'm going to rebuild from here that parabola. And that's all that means. If I were to look at doing, let's say, the absolute value of x plus 2, the absolute value of x has that shape that we talked about yesterday, which is just a V shape. So if I did just the basic graph here of that V shape, you've got the vertex at the origin, and you will look just like that. But then having the plus 2 is going to shift you up 2 units, and it's going to look like this. So when you have something on the outside, it's just a straight up vertical shift, and you do exactly what you see. So like this guy here means we go up 2 units. Well, the one thing that oftentimes will trip students up is when we have something like this, where it says f of x minus h. Now, the weird thing about this is that you've got your this minus h here. And so the h tells us how we're going to be moving horizontally. So this means a horizontal shift. A horizontal shift of h units. So we've got the minus sign right there. And what we've seen before, like we saw this with the center radius form for a circle. The center radius form said x minus h squared plus y minus k squared. So when we were identifying the h and k to form the center, we did the opposite of what we saw. And we're going to do the same thing here. For example, if I do my function, and then I do the absolute value of x plus 3. So this absolute value stuff right here and your x tells you that, again, we're dealing with the V shape. But the plus 3 being on the inside tells me that I have a horizontal shift. So what's happening is that this plus 3 is taking effect before the absolute value occurs. Whereas when it's on the outside, it's just, you do the function, whether it's the square or the absolute value or square root or whatever it happens to be, that gets resolved first, and then you do the plus or minus value. But when it's inside those special symbols, you have to address that first. And so here, even though I see a plus 3 and I'm thinking horizontally, my brain wants to go to the right, but anytime you have that value inside, you're going to do the opposite of what you see. So that's actually going to mean we go to the left 3 units. Now, there are some situations where things can definitely get more complicated when it comes to this. But for right now, we're just going to try to keep things nice and simple. And then in other later math classes, we'll look at how like if I put a number in front of the x inside, we'll talk about what that means. But right now, I don't want to worry about that. So the basic shape here is, again, your V shape for the absolute value. Now, having that plus 3 on the inside, we said we'll go to the left 3 units. So we're going to redo my vertex right there. And then we've got that. So you're just basically grabbing that shape and going 1, 2, 3 units to the left. Likewise, if I were to take the square root function, and I have the square root of x minus 2. The big thing here is the square root of x. And the shape for the square root is that little half sideways parabola. Okay, so if I were just trying to get a nice sketch of that, he would do something kind of like this. Right. Now, obviously, we're going to be looking at getting nice, accurate points, so that our graphs are as nice and neat as possible. This minus 2 on the inside, we're going to do the opposite of that, so we're actually going to go to the right 2 units. So, I'm going to go to the right, click on the right thing, 1, 2 units. There's going to be your starting point, and then you're going to do your graph curving out to the right. And that's all it is. Now, when we do this, if we move it to the right 2 units, we're then going to be rebuilding it from that key point, using those, I think we did this back over here yesterday. So we talked about those parent functions, like there's the square root function you see there in purple, there's the cube root function, the cubing function, the absolute value function. These are all those basic shapes we talked about yesterday. There is your squaring function, and of course, just your linear function or your identity function. All right, so let's put this into practice and let's see what we can do here. So we're going to do f of x is equal to, let's start off with a nice one. Hold on. I realize that my face is going to be in the way. There we go. So suppose this is equal to the absolute value of x minus 2 minus 4. So the absolute value will tell us our shape. So we know that we're dealing with our V shape for the absolute value. So that's the first thing you have to do in all of these functions when you're graphing. Identify the shape. Okay. And then when you know what we're doing with the shape, because essentially we're just going to be grabbing that and moving it around. So this minus 2 on the inside tells me that I'm going to do the opposite. I'm going to go to the right 2. Now I want to be very clear. We're not going to the right 2 because it's absolute value. We're going to the right 2 because it's a minus 2 inside your main function. And so what that minus 2 is doing is that it's causing us to have, you could imagine it being like a delay for where the graph starts. So it starts 2 seconds late, which means it's going to start 2 units to the right. And then we've got this minus 4 on the outside. So we do exactly what that says, which means we go down 4. So what we're going to do is start with the right 2 and down 4, because that's going to tell us where my vertex goes. So remember, your original graph would have had your vertex right here at the origin. We're going to grab it, shift to the right 2 and down 4. So to the right 2 and then down 4 is going to put us right here. This is our new vertex. Now, from here, we are going to rebuild our absolute value function. And the way I like to do this is I like to imagine that this is our new origin. So I pretend that this is my 0, this is 1, 2, 3, and so on. That's how I look at that. From this new origin point, let's build the absolute value. So remember those key points? The absolute value of 1 is 1, the absolute value of 2 is 2, 3, 4, and so on. So just like that. And we have this line of symmetry that goes through the vertex, so we copy these points on the other side. And my recommendation is that you go, or you plot as many points as will fit on the graph, on the grid. Go all the way to the edge. Because remember, we talked about the domain for this yesterday. The domain is going to be the set of all real numbers. So let's connect the dots, remembering that that vertex is going to be a sharp turn. It's not going to be a smooth curve like we would see for the parabola, for the squaring function. All right, so we connect these dots, connect the points, and this is our graph. Now, let's talk about what our domain and range would be, and a few other things. So my domain, remember, the domain is going to be the set of numbers, the set of x values that you used for this graph. And you see this guy goes all the way left, all the way right. So that means it would be all real numbers. So negative infinity to positive infinity. Then our range. So first, let me go back to the domain. The domain for the absolute value function was all real numbers. So no matter where you move your graph, it's still going to be all real numbers. The range for this went from 0 to infinity for the default absolute value. Now, if it's just from 0 to infinity, if you move that up or down, then your range is going to be something different. And you can see that here. Instead of 0 being the low value, it's now -4 because we grabbed it and we moved everything down 4 units. So the range is going to be from -4 up to infinity. A couple of the pieces that we want to talk about here is where are we increasing and where are we decreasing. So as we mentioned yesterday, the increasing and decreasing, we determine that by moving from left to right. What are we doing? Well, you see here from left to right, this guy is going down and then he's going up, right? So those intervals for increasing and decreasing, we're talking about intervals on your domain. So we are decreasing as we're coming from x values of negative infinity up to an x value of +2. So the thing that I think messes with a lot of students here is they think increasing and decreasing is like a y perspective thing. And in some sense it is. But we're trying to determine the range of x values for which as x gets bigger, y gets bigger or y gets smaller. So if I pick any two values in this interval right here, and I put them in order, so this x is smaller than this other one, we're saying our function decreases, which means as x goes to the right, the y is going to be going down. And then we're increasing starting just on the other side of 2, and as x goes toward infinity. That would be our interval for increasing. Now, some other things you might get into would be finding, what are the x-intercepts and y-intercepts, but we're not really asking that right now. All right, so let's try another one. And then we're going to be doing a lot of interesting stuff with these guys. All right, so let me do f of x is equal to x plus 4 squared minus 1. Yes, I see that I'm covering it up with my head. Keep forgetting that's where I got my face. All right. So the things we want to look for are those symbols that tell us my shape, and that's going to be the square. So because of the square, I'm expecting my shape to be a parabola. Now, where is the parabola? Well, looking at what I have inside the squaring function, I see a plus 4. But when it's inside, I'm going to do the opposite of what I see. So this is actually going to go to the left 4 units. The minus 1, which is outside of the main function, outside of the squaring function, it tells me how I move vertically, and I do exactly what I see. So I'm going to go down 1 unit. All right, so that means I'm going to take my key point, my vertex, and go left 4 and down 1. So left 4 and down 1 puts me right here at the ordered pair -4, 1. Now, as soon as I have that guy plotted, I don't need to worry about the left 4 and down 1 anymore. I'm going to see this guy as being my new origin, and I'm dashing out basically a new x-axis and a new y-axis. So that's my 0, 1, 2, 3, and so on. And now what we do is that we rebuild our squaring function. And I don't have to worry about the left 4 and the down 1. That plus 4 inside and the minus 1 outside, I don't worry about that. I've already addressed that by shifting to the left 4 and down 1. So now let's rebuild our squaring function. You can go back and reference the t-table that we had for that. But really, it's as simple as doing this. 0 squared is 0, which is why it's right there. 1 squared is 1, so we're up 1. 2 squared is 4, so we'd be up 4 from that new horizontal that we have dashed in orange. If I go to 3, 3 squared is 9, so this is 4, 5, 6, 7, 8, 9. And we could do the same thing on the left side of this. Or we remember that there is that line of symmetry, and we use that to help us get more points. So I'm just going to copy this guy over. This guy's 2 units, so 2 units over here. 3 units, so 3 units back over here. And now we connect the dots. So a nice, smooth curve for our parabola. There we go. So that's how we would address the shifts there of going left 4 and down 1 for the squaring function. Now, if this is all we do, things are going to get boring very, very quickly. So, let's spice things up a little bit. If I have a negative, where did that go? If I have a negative in front of my function, this negative indicates a reflection. It's a reflection across the x-axis. In other words, we're going to turn our graph upside down. We're going to flip it over. That's all that means. Okay. Another thing to consider is that if I have a multiple, a factor in front of the function, depending on what the a value is, will determine what I'm, how it affects the shape. So, if I'm going to do this. So if the absolute value of that coefficient is greater than 1, then we're going to have a vertical stretch. In other words, it's just a multiplier, and it's going to take whatever you have and stretch it out. So if it's 2 in front, everything's going to be multiplied by 2. So it's going to be growing twice as fast. If, however, the absolute value of that leading coefficient for your function is less than 1, then we're going to have a compression. So let's kind of do an example of this so you see what I'm talking about. I think one of the easiest things to show for the stretch and compression stuff will be with absolute values. But actually, let me first do something with that negative. Okay? If I ask you to graph f of x is equal to negative the square root of x plus 3. So, first identify what the shape is. We've got a square root function, so that means we were dealing with a guy who is this little half sideways parabola like that. Okay? The negative in front means that we reflect across the x-axis. And then the plus 3 happening on the inside tells me my horizontal shift. So I see a plus 3, so I'm going to do the opposite of that, and I'm going to go to the left 3 units. All right, so if we put all this together, let's see what we have. So it's a square root function that has been turned upside down, and it's going to be going to the left 3 units. All right, so it would have started right here, but moving to the left 3 units. So there's my starting point. I didn't go up or down at all, just shifting to the left 3 units. Okay. So if this is my 0, we're going to think about those key values that we had for the square root function. You've got 1. The next one you want to plug in is 4, so 2, 3, 4, and then 5, 6, 7, 8, and then 9. All right. So with the reflection, when I build this, I'm going to be going upside down. So the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. So again, we'll just rebuild it from our new starting point, which happened to be the ordered pair negative 3, 0. And then we just graph this guy, just like that. So hopefully not too bad, right? Again, know the shape that's determined by the function that we see by the square root, and then know what all the numbers do for it. All right, let's try another one. All right, so for this one, let's try f of x is equal to, let's say, 2/3 times the absolute value of x minus 2 minus 5. So the big thing that we see here is absolute value, right? Don't worry about the 2/3, the minus 2, the minus 5. Don't worry about that right now. The key thing is knowing that we're working with the v shape for the absolute value. All right. Now this 2/3. Note that 2/3 is a value that is less than 1. So that means that we're going to have a compression. It's going to be a compression by a factor of 2/3. So when we look at our normal absolute value graph, it's not going to be as steep as normal. It's only going to be 2/3 as steep. Now the rest of this. You got the minus 2 on the inside. It should be a horizontal shift, but we do the opposite of what we see. So that means we'd actually be moving to the right 2 units. And then the minus 5, we're going to be going down 5 because it's outside. It's not connected through multiplication, so that's why we're not stretching by a factor of 5. It's just, here's my function, and then we take 5 off of that. So you have your graph, you pull it down by 5 units. But here's what we're going to do. We're going to first find out where the vertex goes, and that's using the right 2 and down 5. So to the right 2 and down 5 is going to be right here. I'm going to check those off because I've already used them. I'm not going to be using them anymore. This is going to be my new origin. Now let's use this compression. Now, this absolute value is one of the really nice things to do with the compressions, with these fraction coefficients, because you can treat it just like a slope. So as I go from my new vertex, I'm going to do this slope of 2/3. So up to over 3, up to over 3, and so on. Because we have symmetry with the absolute value, I can get points here on the left side. So up to to the left 3, up to left 3, and so on. Again, I'm going to put as many points on here as I can fit so that my graph is going to be as accurate as possible. And so now we just connect the dots, and we have a nice smooth curve. Well, I say curve because it's not a line, right? It's parts of two different lines. Now you might say this doesn't look any different from the absolute value graphs we've already done. Well, let me show you what it would have been like without the 2/3. So without the 2/3, it would have been over here. So the absolute value of 1 is 1, absolute value of 2 is 2, 3, and so on. So without that 2/3, your graph would have been just a little bit steeper. Again, it's kind of hard to see that unless you make that direct comparison. But the dashed red graph is what it would be without the 2/3. The purple one is with the 2/3. All right. Well, I know this is kind of weird, but I'm going to have to cut the stream short today, and I might come back later in the evening to do some more graphing to finish this up. So I apologize for anybody who's expecting to see a whole bunch of stuff today. Again, I'm going to try to come back a little bit later when hopefully things have settled down in the house. But anyway, thank you for anybody who showed up. Please share if you would like to do that. Appreciate it. And until next time, have fun with math.